In this video, I'm going to walk you through the process of imposing design constraints on the lamina stresses if you're working with the composite laminate. We'll be using MSC Nastran's optimization capability. As always, if you have any questions, comments, if you want me to train you, offer guidance, and mentor you on performing an optimization example of your own, feel free to email me. I'll definitely be glad to help you. Now, by the end of the video, this is what we are going to do. We are going to start off with a maximum lamina stress in the one direction of 45,000 KSI for lamina 5. And after the optimization, we are going to make sure that all of the stresses in the one direction for each lamina are under 8,000 PSI. And here at the end, the maximum stress in the one direction is 8,000 PSI for lamina 1. This example is part of a larger video I've gone ahead and already demonstrated. I definitely recommend you view this video if at any time you have a deeper question. But if you do still have questions after viewing this longer video, again, you can email me at this email address here at the bottom right hand corner. In this video, we're going to focus just on design constraints for the stresses in the one direction. So we're going to create 8 design constraints, one for each lamina, that says the stress in the one direction should be less than 8,000 PSI. For this, we are going to use our web app to define this. So let's go ahead and minimize all of these windows and open up my working directory. And this folder is my design model that is complete with design variables and design objective statements already created. All I have to do now is replace these old design constraints with new ones. So let's go ahead and delete those and open up my web app. Let's click on constraints, and this will open a new page where you can create your design constraints. Initially, you'll have a long list of design constraints to select from. What you can do is filter the list by typing in stress. Here, we want to use the stress associated with pcomp or pcomp-g. To create one design constraint, simply click on the plus icon, and this will create in the next table a design constraint. And we said that the stress in the one direction should not exceed 8,000 PSI. So we'll type in 8,000 PSI there. And then we'll go ahead and apply this to element 64. So I'll type in ELEM. I'll type in 64 there. And then for lamina number, I'll type in lamina 1. For the stress item code, this is located in the MSC Nastran Quick Reference Guide. In Chapter 6 item codes, Table 6.3, if you look at the C quad 4 corresponding to the composite, you see that item code 3 is for the normal one direction. So we can use this to specify which stress we want to focus on. So here, let's go ahead and type that 3 in this box. And you'll notice back in the quick reference guide, there was an item code for normal 2. So this would be the stress in the 2 direction. And then you could specify the shear in the plane of the lamina, if you will. So shear 1, 2. You can specify major principal and other types of stresses. But here, I think I've mentioned the ones I want to focus on. So now this completes the creation of a design constraint for lamina 1. We have to do this for lamina 2, 3, 4, 5, and just repeat this until we have 8 design constraints created in the table. So let's go ahead and scroll down a little. And here you see I've accidentally created an additional design constraint. You can click on the X icon and that'll delete that constraint. Now let's go ahead and fill these in. We'll use the same item code as before. The 3 corresponds to the normal one direction. and then we are going to specify the same constraint on element 64. If you're watching this and you're wondering why element 64, definitely refer to the video I mentioned earlier in this presentation, or alternatively look for another video just called, let's see, design constraints on failure index. That's the other video, and the other one is design constraint on composite strain. And again, you can find those all throughout my YouTube channel. Now we want to do this for laminate 1, and then we'll do this for laminate 2, 3, 4, all the way down to laminate 8. So that completes the creation of my design constraint, where I'm restricting how high the stress 1 can be for each lamina. So I've taken the statements here from my web app, and I'm going to go ahead and paste those in my design model. And now what I can do is use Nastran to perform the optimization. So let's go ahead and do that now. And while that's happening, a quick reminder, if you want support, you want training, you want access to this web app that really makes the process of performing optimization simpler, reach out to me and we can definitely have a discussion regarding your needs. Here on this slide, I'm just summarizing what I expect to have after the optimization. I expect the mass to go from 1.6 inches to 0.16 inches. And the way I got these results, I didn't have knowledge beforehand that this is what I was expecting. I already did this example beforehand, so that's why I have the notes here. Here on the left is the initial layup. Here on the right is the final layup of the final design, the thickness, and so on and so on. Now let's go ahead and minimize this window and see if MSC Nastran's finished. And yep, it's finished now. So let's go ahead and wait here. And here I see that I'm having an issue with memory. Yes, I am. The reason I'm having an issue with memory is I'm using a virtual machine, as you may have seen earlier in the video. And I purposely gave this machine a very small amount of memory. And that's because just simply my host machine doesn't have too much memory. So I'll run into situations like that where when I have all these programs open, it runs into that situation. So let's go ahead and close one application and run the optimization again. And while that's happening, let me stress one detail on this. I definitely want you to walk away from this video with some really useful information. Here in this plot is a progression of the normalized constraint history. If you're asking what normalized constraint history is, again, I have another video in my YouTube channel. You could refer to that for details on what this normalized constraint is. Each design cycle will have one design constraint that violates its constraint the most. That constraint, in a way, governs, it dictates the following design cycle. So in that design cycle, the optimizer will work on satisfying that leading constraint, as well as the other constraints that are also violating the constraints. So here, for the initial design, you see that the stress 1 of lamina 5 was beyond the 8,000 psi. There's a reason why this one's kind of what's the word I'm looking for? This value, or this design, or the leading design constraint for number 1 was not considered because some of the constraints were not retained. And just to make this video brief, I'll glance over why that happened. But again, if you do have a question, email me, leave a comment below in the video, and we can answer it and have a discussion there. In the next design cycle, you can see that the stress 1 of lamina 1 is now leading the design cycle process. And then after that, you see stress 1 of lamina 1 is actually the leader for the next design cycles. So that's one detail I want you to walk away from the video with. Now let's go ahead and look at my results and make sure that the bottom of the F06 file says that the optimization was successfully performed. So perfect, that's what I have here. Let's go ahead and look at the results first. So at the very beginning, we had a mass of 1.59 slinches, and then by the end, we had a mass of 0.159 slinches. So this was what I was expecting. My thickness, or the values for the design variables, are listed here. I see that I have a value of thickness for 0.001, and my plies are now 80 degrees. So let's go ahead and review that in the PowerPoint. And then I'm close to concluding this video, so this will go very briefly. So here on the left are the initial values, and here on the right are the final values after my optimization. You see that after design cycle 1, that's where, for the most part, the orientation angles were significantly modified. After design cycle 1, you can see that the orientation angles are not changed as much as they were in the first design cycle. For the thickness, we see that there's sort of an opposite effect there. After design cycle 1, we see the change of thickness go from this value to the new value. And the value here is not actually 0. It's just, I said just show me show me nothing after a decimal point, so it just showed me 0. Here, it started off with the value of 0.01. It went down to maybe 0.008 inches, and then it went all the way down to possibly 0.001 inch at the very end. So you can see that after design cycle 1, it was the thickness that was being modified the most. And now let's go ahead and view our results in Patran. So after the optimization was completed, a new result file that was created, and I can attach this to any pre-post processor that supports the MSC Nastran result type. So just bear with me while I go ahead and attach my result file. And this result file is special because it has both the initial design results and it has the results of the optimized model too. So let's go ahead and import these results right now. And I'll go ahead and view the stress tensor for element 64. Let me go ahead and re-import those result files. And we expect the stress tensor for the one direction to be no more than, let's see, what was it, 8,000 psi. So let's go ahead and confirm that is true here. Let's go ahead and select just element 64. Okay, perfect. So here, let me also fix the scaling just so it looks a little better for you. Here we go. So here you have it. Here's the result for lamina 8. You can see that in the one direction, the maximum stress is 8,000 psi. And let's go ahead and view one of the stress values for one of the 60-degree plies, so lamina 6. Here in the one direction, the stress is well under the limit of 8,000 psi. So you can see that the ply 8, and most likely ply 7, let me see what the stress is in that ply. Right, this is 8,002. So you can imagine the plies in the outer sides of the laminate, so the top 2 plies and the bottom 2 plies, these all have sigma 1 values of 8,000 psi. So those were actually influencing and dictating the optimization process. So with that, we are essentially at the end of the video. Hopefully you found this video information useful to you. If you have any feedback on how to improve this video or any other one of my videos, definitely leave me a comment below or send me an email. I'll definitely reach out to you and send you a nice reply. If you want more training, if you want guidance, if you want access to this web app that makes the process of optimization really simple, again, email me. And with that, a big thank you to everyone for watching.